Hey folks, it's Christmas season, which means I'm dressed up like Santa Claus and snorting mountains of powdery white cocaine. Since I've got some energy, I want to show you how the tensor product can be used to study linear transformations of vector spaces and prove an important special case of the famous Skolem-Noether Theorem. If you need a refresher on the tensor product, check out my videos on it. Before diving into the theory, we begin with a question. I've seen this type of question asked numerous times on the Q&A site MathStackExchange, usually getting downvoted and closed by autistic users because of minor grammatical or spelling errors. Let f n by n be the algebra of n by n matrices over the field F. In this video, algebra just means a vector space with a bilinear multiplication, in this case matrix multiplication. Consider the matrix transpose operation on this algebra. We know it's linear, and it reverses products, so it's what's called an anti-endomorphism of the algebra. The question is, are there any other interesting anti-endomorphisms of this algebra? By definition, the zero operation is not interesting. We might also think of the matrix inversion operation, but it's not defined for all matrices, so it's out. The whole anti-element of this question is actually slightly annoying, so let's eliminate it. If F is an arbitrary anti-endomorphism of the algebra, then if we define H by precomposing transposition, we get an endomorphism. That's because H of AB equals f of B transpose A transpose, which equals f of A transpose F of B transpose, which equals H of A, H of B. Conversely, we get f back by precomposing transposition again, since transposition is an involution. So this reduces the question about anti-endomorphisms to the corresponding question about endomorphisms. What are the endomorphisms? Well, we know for any invertible matrix P, conjugation by P, viewed as an operation on the algebra, is an endomorphism. In fact, it's an automorphism since it has an inverse, which is just conjugation by the matrix P inverse. Such automorphisms are called inner automorphisms. Are there any other interesting endomorphisms of the algebra besides conjugation? It turns out the answer is no. We have a theorem. Every non-zero endomorphism of the algebra of n by n matrices over a field is an inner automorphism. This is an important special case of the more general Skolem-Noether theorem. As a corollary, we have that every non-zero anti-endomorphism is just conjugation with transposition. So the answer to our original question is that up to change of basis, transposition is the only interesting linear operation on matrices that reverses products. We're going to prove this theorem in this video by using the tensor product to study linear transformations. In doing so, we set aside matrices and go coordinate-free, just the way God intended. So let V be a finite-dimensional vector space over F, and let V star be the space of linear forms on V, which is dual to V under the usual pairing operation, which I'm denoting with angle brackets and also call a scalar product. Finally, let LV be the algebra of linear transformations of V under composition. Then the map from the Cartesian product set V star times V to LV, defined like this, is bilinear. Let's take a moment to digest this. First, the vector V star here is an arbitrary element of the space V star, and the vector V an arbitrary element of the space V. The vector V star is not the result of applying a star operation to the vector V. The transformation on the right-hand side here takes as input a vector in the space V, computes its scalar product with the vector V star, multiplies that scalar by the vector V, and returns the resulting vector, which is also in the space V, as output. This is indeed a linear transformation since the scalar product and scalar vector multiplication are both bilinear, and the transformation depends linearly on each of the vectors V star and V for the same reason. The transformation is of a very special type. Notice if either of the vectors V star or V is 0, it's just the zero transformation. Otherwise, it's of rank 1, with image equal to the span of the vector V. Now, by the universal property of the tensor product, this bilinear map induces a linear map from the tensor product space V star tensor V to LV. We know that the linear map is surjective since LV is spanned by rank 1 transformations, so it's also injective since the dimensions of the two spaces are the same. Therefore, we can take LV to be the tensor product space V star tensor V if we define the decomposable tensor V star tensor V to be the corresponding linear transformation. Then every linear transformation of V can be written as a sum of decomposables like this. This representation is not unique. However, we can assume that the vectors involved are linearly independent by taking the number of decomposables to be minimal. Indeed, if there were a linear dependence relation among the V's, for example, We could express one v in terms of the others and use bilinearity of the tensor product to get a representation with one fewer decomposable. It's also fairly easy to see that the minimal number of decomposables is just the rank of the linear transformation. I encourage you to pause the video and check both of these things. But why do we care about all this? That is, why do we care to represent linear transformations as tensors? There are multiple reasons. Mathematical reasons. One is that we can apply general facts about tensor products to linear transformations. Another is that we can often reduce questions about arbitrary linear transformations to questions about decomposable ones, and tensors make this convenient. For a simple example, it's easy to see that the spectrum of eigenvalues of V star tensor V is the scalar product V star times V together with zeros. So the trace, which is the sum of the eigenvalues, is just the scalar product. Since trace is linear, the trace of any linear transformation is a sum of such scalar products. In fact, this gives us a new perspective on the trace. It's just the unique linear form corresponding to the scalar product via the tensor product. For composition of decomposables, we have the rule seen here. That's because V star blank V after U star blank U equals V star times U star blank U times V. Pulling that inner scalar U star blank out and to the right, we get V star times U star blank V, which is what's above. Now any composite of transformations can be computed from this rule using bilinearity of composition. This is sometimes called the composition algebra and is powerful. However, it's important to remember that this is just one definition of the tensor product for V star and V. We saw in a prior video that we can also take a tensor product space for V star and V to be the space of linear forms on V star tensor V, with the scalar product of decomposables defined like this. We also make use of this tensor product in this video. We write it with a dot instead of a cross to visually distinguish it, but we still use the word tensor. Now, in order to tackle the Skolem-Noether theorem, we need to study linear transformations of linear transformations. The notation gets a little more complex, but like Paul Erdős once said, that's not a problem when you're speedballing. We write A for LV. Then LA is A star tensor A, where A star is the space of linear forms on A, and the tensor product is defined to give linear transformations of A. But A itself is V star tensor V, so this expands like this. The space of linear forms on V star tensor V is the other tensor product space we just defined, so we get this. The tensor product of decomposables is defined like this. Remember here, the tensor V star tensor V is a linear form, while U star tensor U is a linear transformation. The notation helps us keep that straight. Now, it's totally possible to study LA directly using this tensor product. However, for our purposes, it's more convenient to use a slightly different one. I'll first define it and then explain what it does. By the universal property, there's a natural isomorphism between the tensor product spaces seen here, which maps decomposable tensors like this. Notice the isomorphism just swaps the vectors u and v, that's all. We write the induced tensor product with a square to distinguish it, but still use the word tensor. It follows that LA can be taken to be a tensor A, with the new tensor product of decomposables defined like this. Of course, the burning question on any sound mind is what is phi tensor psi for arbitrary transformations phi and psi? The answer is that it's bicomposition with phi and psi, postcomposition of phi and precomposition of psi. Remember, this is a linear transformation of linear transformations. It takes as input a linear transformation, postcomposes phi and precomposes psi, and returns the composite as output. In particular, inner automorphisms have the special form phi tensor phi inverse for invertible phi. How can we actually prove this? By reducing to decomposables. It follows from definitions that the tensor product is bicomposition when all three linear transformations involved are decomposable, as seen here. I'm not going to read all of this shit out loud, but you should pause the video to check it. The key thing to observe is that this identity depends linearly on each of the three decomposables, so the identity extends to all transformations. Now, since we have a tensor product, every linear transformation of A can be written as a sum of decomposables. And we may assume that both of the multisets of linear transformations of V involved are linearly independent. We can also apply other general facts about tensor products. For example, suppose that a sum of decomposables of phi's and psi's equals 0. Then if the phi's are linearly independent, the psi's must be 0. And dually, if the psi's are linearly independent, the phi's must be 0. We proved this fact for arbitrary tensor products in a prior video, but in this context it's telling us something interesting about bicomposition of linear transformations. We can use this fact to prove Skolem-Noether. To that end, suppose H is a non-zero endomorphism of the algebra A, so H is linear and preserves composites. Then we can write H as a sum of decomposable tensors, and we can assume both multisets of linear transformations involved are linearly independent. Now, for arbitrary phi and psi, 0 is equal to this quantity since H preserves composites, which equals this quantity derived from the tensor representation of H, where the indices I and j range over the number of terms in that representation. By distributivity with the first set of parentheses, that equals this quantity. We notice that we now have a difference of two sums over I which start with phi I phi. That equals the single sum seen here. The key thing to remember is that phi and psi are completely arbitrary. Since phi is arbitrary, we actually have a sum of decomposable tensors equal to 0. And since the phi I are linearly independent, the second components must be equal to 0. Looking closely at one of those components, we see that we have psi psi I minus a sum over j which has psi psi j on the right. We can express the whole thing as a sum over j using a Kronecker delta times the identity transformation as seen here. And we have that this thing is equal to 0 for all I. But now since psi is arbitrary, we actually have a sum of decomposable tensors equal to 0, one sum for each I. And since the psi j are linearly independent, all of the first components from these sums must be equal to 0. This is juicy. Taking I equal to j in these equations, we obtain that psi I after phi I is the identity transformation, and hence phi I and psi I are inverses of each other for all I. On the other hand, for I not equal to j, psi I after phi j is the zero transformation. How is that possible? Well, remember that I and j range over the number of terms in the tensor representation of H. Since H is non-zero by assumption, and hence the algebra A and the vector space V must be non-zero, so the zero transformation of V is not invertible, this is only possible if H has only one term in its tensor representation, and I and j are always equal to 1. And since psi 1 is the inverse of phi 1, H is just phi 1 tensor phi 1 inverse. So H is an inner automorphism, which is exactly what we wanted to prove. Isn't that a cool proof? As I mentioned earlier, the full Skolem-Noether theorem is more general, but I'm starting to crash, so you'll need to go look it up. Here are the references I used while making this video. Thanks for watching.